In this video, we're going to continue working through 6.5, and we have another technique to evaluate the normality of sample data. So to remind you, what we're talking about is maybe we have a sample data set and we wish to determine an answer to the question, do these fit a normal distribution? Our first technique was to fit a bell curve to the sample histogram, which is something like eyeballing whether the data follow this normal distribution, but perhaps we can be a little bit more precise. So for that, we're going to leverage the empirical rule, which I'll remind you is a statement about what happens when we have approximately normally distributed sample data and how far away these data are from the mean. So if we have a sample mean x bar and a sample standard deviation s, then there's three parts to the empirical rule. And all of this is to say that this assumes that we have normally distributed data, but we can use it backwards to confirm that our data are probably from a normal distribution. So about 68% of the data are within one standard deviation of the mean. So in other words, about 68% lie within x bar minus s and x bar plus s. The second statement tells us how many data values fall within two standard deviations of the mean, and for that we find about 95% of data are within two standard deviations of the mean. So between x bar minus 2s and x bar plus 2s. The last one tells us about what happens when we're within three standard deviations of the mean. In this case, almost all of our data, so 99.7%, are within three standard deviations of the mean. So if you don't remember this, this is something that we briefly talked about in Chapter 3, and it's a way for us to think about the location of data in a distribution. Why this is so helpful is because this goes two ways. So one, this is true if the sample data fit a normal distribution. Two, if our data follow the empirical rule, then we have fairly strong evidence that we have a normal distribution. Of course, there is more to be said here about how do we confirm that this actually is a normal distribution that we're taking data from. You probably would want to pair this along with a histogram. So all of these heuristics that we're going to apply in this section, we can use in conjunction with each other. So for the sake of illustration, we'll work with the same example that we did last time, where we were looking at SAT scores, and we want to examine those data by the lens of the empirical rule. So unfortunately though, since we had, our roadblock here is we don't have the raw data, so we have to estimate x bar and S, okay? So because we have a frequency distribution, we actually can do this using one of the techniques from chapter 3, where if each class C, we represent FC as the frequency, and XC is the class midpoint, then we can estimate X bar using a weighted mean. So for each class, we're going to compute the frequency times the class midpoint, add those all up, and then add up the frequencies, which should just be the sample size. So as a note, this should just be equal to the sample size. And you can pause here and go back to the previous, go back to the distribution itself and examine, first of all, figure out what the class midpoints will be using the class midpoint formula. And then the relative frequencies are, those are fine. We can use those as well. Otherwise, if you really wanted to work with the frequencies, you would just have to scale them up by multiplying each relative frequency by the sample size. But that's not necessary. Going back then to the calculation, if you want to pause now and work through that calculation, we do get approximately 1113.95. And similarly, we can do another calculation for the standard deviation, where we're going to again do a weighted mean. So for each class, we're going to multiply the frequency, or relative frequency, by the square deviations of the class midpoints. So how far away those are from the mean, square those, multiply by the frequencies, and then add those all up. And divide that by, again, the sum of the frequencies, which again should just be equal to the sample mean. Pause again if you'd like, work through this calculation. One helpful hint I have for all of these is if you have access to technology, which you almost certainly do, if you have Google Sheets or Excel and are comfortable working with the formulas and the functions in either of those programs, you can make short work of any calculation that has sums, because you can use the sum formula where you just insert the data range. And that'll make it much easier to work through any of the summations that we're working with here, rather than putting them in one by one into a calculator. And so for this, I get that this is approximately equal to 250.6. So roughly then, we can imagine that for our data set of SAT scores, our mean is roughly right here, and each standard deviation out, so 113.95 plus 250.6 and 1113.95 minus 250.6. And so this range right here is actually from 863.35 to 1364.55. And so that's this range right here is the within one standard deviation of the mean, approximately, because we approximated everything. So we understand that this range is actually narrower than the actual middle three classes. So it's okay if the actual proportion of data in our three classes is higher than the 68% heuristic. Here, though, because this corresponds roughly to the middle three classes in our distribution, so what lies in this? So data that fall within this range, we have the 800 to 999 class, the 1000 to 1199 range, and the 1200 to 1399 class. Now this is imperfect because some of them may fall outside of this, but we're estimating here. So if we add up the three relative frequencies, which are 0.2242, 0.3333, and 0.2303, we get 0.87878. Okay, so remember what the empirical rule says. The empirical rule says about 68% lie within one standard deviation. What our actual calculation revealed was that we have about 79% lie within one standard deviation of the mean. So this is higher, but again, remember, because we said that we're actually, we actually have calculated a narrower range than the actual middle three classes, and overestimation is actually okay. That said, then we would want to find the match for the within two standard deviations. So again, the mean is 1113.95 plus two standard deviations yields about 1615.15, and minus two standard deviations yields about 612.75. This is roughly every class that falls between these two values. So within two standard deviations, and the classes that lie in this interval are everyone except the last two. So all classes except the very lowest one, which is, what was that, 400 to 599, and the very top, which is 1600. And so we get that this amounts to 1 minus these two relative frequencies, and that is going to be 0.9455, which is pretty close to our empirical rule standard. Our empirical rule standard says that's 95% that lie within two standard deviations, and the actual is roughly, well, if we round to a whole number percentage, then this is, again, within 2 standard deviations of the mean. So overall, pretty solid. The very last one, we would want to compute the bounds for within 3 standard deviations, but without ambiguity. This does cover all of the classes. And by the empirical rule, we're supposed to cover 99.7%, which are within 3 standard deviations of the mean. And our actual will actually be 100%. So altogether, first of all, we have done quite a bit of estimation because we did not start with a raw data set. We started with summarized data. With a raw data set, it's much easier to do this precisely. And secondly, even though we're not fully on the nose with some of these are actually not too bad. The only part that is challenging for us to assert that this is a normal, that this comes from a normal distribution is the very first part of the heuristic.